Greetings. In the name of our team, we would like to present crack path and fracture analysis in very high cycle fatigue under biaxial loadings. We're going to begin our presentation by making a small introduction to ultrasonic fatigue technologies. So to better introduce the two methods we're going to talk about here in this presentation. First, cruciform applied to ultrasonic technologies, their theory, concept, and setup. We're going to present the experimental setup and the associated fatigue results. From that, we're going to make a fracture analysis of the fatigue results obtained of cruciform specimens. Finally, we're going to make a small introduction to the tension torsion ultrasonic fatigue machine developed by our team and some fatigue results associated to this machine. And finally, we're going to talk about the technical conclusions of both methods. Ultrasonic fatigue testing machines use resonance as a way to apply high-frequency fatigue. The objective of these machines is to study in the very high cycle fatigue regime. This is established between 10 to the power of 6 to 10 to the power of 9 cycles. If we have here the tension compression machine where we apply the piezoelectric transducer that has as a standard 20 kHz. Then he uses a booster and a horn that amplify the displacements coming from the piezoelectric transducer and induce the resonance of the specimen that has the ability to have a high enough stress amplitude in one fatigue testing region, its center. Knowing that ultrasonic machines use resonance as a way to achieve the high frequency fatigue, we need to design cruciforms that have a resonance mode at the working frequency and with the desired stress combination at one desired fatigue testing region. So with the model analysis of cruciform geometries, we were able to achieve two different geometries: the in-phase tension seen here on the left and the out-of-phase compression tension seen here on the right. Now we can see here an animation of the tension in phase and the out of phase compression tension, where we can see that when in phase the arms stretch and compress simultaneously, where in the out of phase, while one arm stretch, the other compress, and vice versa. So the ultrasonic setup is very similar to tension compression as shown in the first slide. Here we have the piezoelectric transducer, the booster and the horn, which amplify the displacement coming from the transducer, and then the specimen that is excited with the actual displacement provided by the horn. Then we can excite the out of phase and in phase TT and CT to achieve the out of phase pure shear and the in phase equal biaxial. Now all cruciform geometries follow one optimized geometry made from Batista and its colleagues on the paper that we present here on the left corner of the slide. Now this geometry was optimized to have a higher stress combination at the center, the fatigue testing region, and ensures the intended actual stress combination in the same fatigue testing region. Now we made all specimens from the same aluminium, the 6082 T651 aluminium, and made CT and TT specimens here presented on this slide. Now the followed experimental setup is very similar to the uniaxial tension compression ultrasonic fatigue machine. Instead of measuring just one displacement, we measure two, the vertical, as we call it, direction, the Y displacement measurement, and the X displacement measurement. We also made strain analysis where we measured the strain in the fatigue testing region using a rosette strain gauge in the center of the cruciform specimen. From the experimental setup, the cruciforms were applied to the ultrasonic fatigue machines and tested until failure. Both TT and CT specimens presented crack initiation at the specimen center, the fatigue testing region, and from that the crack path was analyzed as well as the crack initiation angle. The crack initiation angle was measured from the x-axis, as here presented. In this case, the axis comes here and the crack initiation begins with an angle. Now, comparing TT and CT specimens, all TT specimens presented a single crack propagation, here with a 54 degrees roughly of crack initiation, while the CT specimens presented both single and cracks with bifurcation behavior. Now, the bifurcation behavior started mainly at higher angles of crack initiation, where there is a small crack propagation followed by bifurcation. After some propagation of the bifurcation behavior, there is a chaotic behavior until the highest cross-section area. In single propagation CT specimens, the crack initiation angle is smaller, here around 24 degrees, and it follows roughly this behavior here drawn. Now, because ultrasonic fatigue testing machines are resonance dependent, we cannot achieve a fully fractured specimen. As the fatigue fracture grows in the specimen loses rigidity and therefore it loses frequency, making the setup losing the resonance frequency in the working frequency of the transducer, and therefore the ultrasonic fatigue machine comes to a stop. To have access to the fatigue fracture, the specimen must be put under a classical machine to make the final fracture of the specimen and therefore having access to the fatigue fracture. In this case, we put the cruciform specimens under tensile forces in the classical machine and obtain fully fractured specimen. Now, having access to the fatigue fracture, we need to cut samples of the specimen in order to be able to introduce the samples in the scanning electron microscope to make a SAM analysis. So in this case, we cut the specimen, a sample of the specimen, here in this case a TT specimen, for the SAM analysis. Now, having access to the fatigue fracture surface and making a SAM analysis, we make first a general observation of the fatigue fracture surface. We can clearly see there are three stages of propagation. The first one and the main one of main interest were happening on the small cross-section area of the specimens. This is where the stress combination is the desired one of study, and this is where we're going to make a deeper analysis. The second and the third stage present a much higher propagation rate and the changes in fatigue fracture morphology associated with changes of stress applying damage to the specimen. Also, by a general view of the fatigue fracture, we can see in all cruciform, in all stages of propagation, microvoids present in the titanium tested. Now, for TT propagation stage 1, we see surface crack initiation in the small cross-section area, showing striations associated with crack mode 1 propagation, and also microcracks across the entirety of the fatigue fracture surface on stage 1. Now, observing the CT and then comparing it to the TT, we can clearly see there are shear type fracture on the CT specimens. We see especially the mixed mode between mode 2 and mode 1 crack propagation, especially on the surface, where in the interior of the crack we can sometimes see mode 2 flat surfaces showing signs of rubbing. Now, after stage 1, there are stage 2 and 3 with completely different fracture surface morphologies. Looking first at the CET, the stage 2 presents crack mode 2, and stage 3 presents a crack mode 1 with tensile dimples that reflect a ductile failure. Stage 2 of the TT is very similar to the stage 3 of the CT with the dimples tensile damage, while the TT stage 3 now presents elongated dimple type fracture associated with shear damage. Now, all 2 and 3 stages of TT and CT specimens show a much higher crack propagation to the stage 1. Now, the second biaxial very high cycle fatigue method applied is the tension torsion solution, here developed by our team. We apply the same piezoelectric transducer exciter to the same booster, but we change for a special horn that not only excites the specimen in an actual displacement, but it also provides a rotation displacement, thus exciting the specimen in both an actual and a rotational resonance mode, achieving thus an in-phase tension torsion stress combination that is adjustable. Here we can easily increase torsion or tension relation between the tension and torsion. Now, just as cruciform specimens, tension torsion specimens, after reaching a certain size of fatigue fracture, they lose resonance and they require to be fully split up by classical means. This is the only way to have access to the fatigue fracture surface. Now, several tension torsion specimens were tested with different shear and axial ratios. All tested specimens presented surface crack initiation, and as the higher shear tensile ratio, the more considerable torsion fracture surface marks we can see. We can clearly see for a considerable shear and axial ratio marks associated with shear damage, much more pronounced than when the actual tension is much higher than shear tension. Now, the torsion fracture surface marks are associated with this staircase fracture shape. And here, in the case of 1.24 shear and axial ratio, is quite predominantly the effect of shear in the entirety of the surface fatigue fracture. Now, to all specimens, we also measured the crack initiation angle in relation to the axis of the specimen. Can clearly see an increase of the crack initiation angle in respect to the axis for higher shear and axial ratios. Now for conclusions, first focusing on cruciforms. Cruciform fatigue testing was successfully reached. Now two different cruciform specimens were tested, in-phase tension or TT and out-of-phase compression tension CT. Both types of cruciform specimens achieved fatigue fracture successfully, obtaining a completely different fatigue fracture surfaces. The TT presented a mode 1 crack propagation, while the CT specimens presented a mixed mode of 1 and 2 crack propagation, with a significant shear damage. Regarding tension torsion method conclusions. All tested specimens guaranteed the highest stress amplitude in one single fatigue testing region, the pretended and denoted main throat. All fatigue fracture specimens presented surface crack initiation, which was predictable. Now, looking at the shear axial ratio, as the shear and axial ratio gets higher crack initiation angles are obtained and more predominant torsion fatigue marks are obtained associated with a higher shear damage. In the future and ongoing work, SEM imaging will improve the fatigue fracture surface analysis, showing all present crack modes throughout the fatigue fracture surface. And thus conclude our work on crack path and fracture surface analysis in very high cycle fatigue under biaxial loadings. And on my behalf and on behalf of our entire team, we'd like to thank you for your attention.